Now let's talk about problem solving using recursion. We are now going to jump into this topic in a purely computer science aspect. First, some definitions. One more time, let's define recursion. Only this time, let's use one of my very favorite resources for all things programming, geeksforgeeks.com. They say the process in which a function calls itself directly or indirectly is called recursion, and the corresponding function is called a recursive function. Using recursive algorithm, certain problems can be solved quite easily. I like that definition a lot. It gets down to the point about how to use recursion programmatically. Another definition that we'll need in order to understand recursion would be for base case. Again, using the geeksforgeeks.com definition, in the recursive program, the solution to the base case is provided and the solution of the bigger problem is expressed in terms of smaller problems. Meaning, the base case is the solved version of the problem. Once the function arrives at this case, it can now sum up all the activity that had previously taken place. I'll show you what I mean in a moment. According to Manuel Sanchez, an author introduced in the first video, the base cases correspond to scenarios where the function's output can be obtained trivially without requiring values of the function on additional arguments. For the Fibonacci sequence, a very popular algorithm for describing recursion, the base statements are f of 1 equals 1 and f of 2 equals 1. These are the very start of the formula, and I will be describing it in detail as I walk you through the program later. Ever heard of factorials? You remember from math class? Say you have the number 5. You multiply 5 by 4, 4 by 3, 2 by 1. This is also a very popular case for recursion, and you can see why. We'll also be going over this in just a moment. When programming and thinking recursively, our main task will consist of providing our own recursive definitions and functions. While the first step usually involves establishing the base case, the main challenge consists of describing the recursive cases. I find it helpful when learning a new skill to watch others solve a problem over and over, or do that task over and over. Recursive problem solving isn't magic. It is a developed skill. Let's jump into a couple programming examples in order to better understand what recursion is, how we develop our solution from our problem domain, and how we know our base case. The first program is going to be the factorial function. Let's think about how the factorial pattern works. What number do we want to work out our factorial recursive problem with? In recursion, it is a good approach to think about these topics on a very small scale. Let's start with 3. If I multiply 3 by 2 by 1, we get 6. Okay, what pattern do we see? What number do I subtract from 3 to get 2? How about from 2 to get 1? Is this the same pattern as our numbers get bigger? Will this work if I have 4 as my largest number? We can say that 3 minus 1 is 2, and 2 minus 1 is 1. If we then call 3 n, then we actually have our formula. N minus 1 factorial equals n minus 1 multiplied by n minus 1 multiplied by n minus 1, and so on and so forth. Well, let's write this out. I'm going to be writing my program in C++. I love this language because it is extremely fast and flexible. It is especially good for writing recursive functions. Okay, now that I have my program open and all the necessary boilerplate code in place, let's begin. We're just going to call it something very simple. We'll just call it factorial. And just a hint, we're going to return an integer in this function. We know that the formula was n minus 1 factorial. So we know that there's going to be a need for one parameter at least. And since we're returning an integer, we're going to pass in an integer. And I'm going to call it n since that was our number that we had decided. Let's go back to our definition from Geeks for Geeks about what a recursive function is. The process in which a function calls itself directly or indirectly is called recursion, and the corresponding function is called a recursive function. So that means that we need to call our function within our function. Let's do that in our return statement. So I'm going to say return, and then I'm going to type out my name of my function. So our formula was n minus 1 times n. So let's pass in n minus 1, and let's multiply that by n. So we're saying n times factorial n minus 1. So when we pass in a 4 right here, it's going to copy that 4 to the n and then multiply a call to factorial again where we pass in 4 but we minus 1. And so that will call 3. So we'll say 4 times factorial of 3, and then it will again jump to the top of this, and this will be 3, and then we'll pass in 3, and we'll multiply by 3 minus 1, which is 2, so factorial 2, jumping up to the top of this header again, the function header. Then we will pass in 2, and n will copy down here to 2. We'll do 2 times factorial 2 minus 1. Should we try this? Let's call our factorial. Let's use the number 4. Okay. So let's call this function now. Uh-oh, I'm having a problem. Let's go up here. There we go. What do we see here? We see hundreds of calls to this factorial function. I'm going to click stop here. What's happening? What's happening is called a stack overflow. A stack overflow occurs if the call stack pointer exceeds the stack bound. Well, what is the call stack? It is a stack data structure that stores information about the active subroutines of the computer program. So let's talk about this stack. Looking at this illustration, we can get a mental image. Here we have the main program, and say we want a factorial 4. In order for it to work correctly and have its own local variables, another stack frame is added, and it's going to return the answer to factorial 4. Then factorial 4 says, I can't know what factorial 4 is until I figure out what factorial 3 is. Then factorial 3 says, well, I cannot know what factorial 3 is until I know what factorial 2 is. So another stack frame is added in order to do this computation. Factorial 2 then passes in factorial 1. This is the base case that I mentioned earlier. This is where we want to stop. This is where we add our base case. If we don't, our function will be called recursively forever. So our base case is f of 1 equals 1. If we pass in 1, we return 1 and not a function call. Now when 1 is returned to factorial 2 now returns its answer to factorial 3. Then factorial 3 can return its answer to factorial 4. Thus the final function is returned and we have our answer. However, each answer must wait for the latter answer to return one at a time. So let's add this to our code here. And notice my compiler was giving me this clue early on, saying all paths return this function will call itself, saying you're never going to get out of this function call. So let's add our base case. We'll say if n is equal to 1, then return 1. Now let's call our function. There we have it. When we passed in 4, it did the math for us. It went through all the stack frames, and now we have the answer 24. Let's print out and see if we can't see each of the answers. There we have it. 4 times 3 times 2 times 1. So 4 times 3 is 12. 12 times 2 is 24. And 24 times 1 is 24. So there we have our factorial problem. The next program that we're going to get into is the Fibonacci, and we're going to do that in the next video.